Hi everybody, so we're going to do this PowerPoint on chapter 4 where I'll do some videos on how to do the homework and things like that, and that'll also help you by showing you how to use the calculator to do all this. And so we're going to be describing the relation between two variables, and we're going to do that through graphing. Some of the main points of this chapter we're going to talk about are correlation and regression lines. So hopefully after this video you'll be able to draw and interpret scattered diagrams, or by the end of this video series describe the properties of linear correlation coefficient, compute and interpret the linear correlation coefficient, determine whether a linear relation exists between two variables, and explain the difference between correlation and causation. The response variable is a variable whose value can be explained by the value of the explanatory or predictor variable. A scatter diagram is the graph that shows the relationship between two quantitative values measured on the same individual. Each individual in the dataset is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis, when the response variable is plotted on the vertical axis, the y-axis. Drawing and interpreting a scatter diagram. So the data here shown on the right is based on a study for drilling rock. The researchers wanted to determine whether it takes time, or whether the time it takes to drill a distance of 5 feet in rock increases with the depth at which the drill begins. So depth at which the drill begins is the explanatory x, and time in minutes to drill 5 feet in response is the response variable y. So we draw the scatter plot, and it looks something like the following. Okay, and so we want to find out if there's some kind of correlation between these things. And so if you look up here, the response, various different types. Notice that the response for part A is sort of increasing. It's going upwards to the left to the right. The next one on the right is downwards facing. It's negative response, negative correlation. We have a nonlinear, which is like a parabola. Another nonlinear, which is called cubic in math. And then no correlation is when they're just kind of everywhere and you can't tell what's going on with it. Okay. Two variables that are linearly related are positively associated when the above average values of one variable are associated with the above average values in the other variable, and the below average values of one variable are associated with the below average variable values of the other variable. That is, two variables are positively associated if whenever the value of one increases, the value of the other one increases. Two variables are said to be linear or linearly related are negatively associated. Obviously, that would be the opposite. If the two variables are negatively associated, whenever one of the values increases, the other value decreases. Okay. The linear coefficient, or the Pearson product moment correlation coefficient, is the measure of the strength and direction of the relation between the quantitative values. The Greek letter rho represents the population coefficient, and the r represents the sample correlation coefficient. We present only the formula for the sample correlation coefficient, so we'll use a calculator to do this. This is how you would solve it normally. You're going to use the sum of your x, each individual thing, minus the mean over the standard deviation of x. And it's a lot of calculations and things like that. Since you're going to use a calculator, you probably won't have to worry about this. Properties of the linear correlation coefficient, it's always between -1 and 1. If r is equal to +1, then it's perfect positive linear correlation between the two variables. If r is equal to -1, then it's a perfect negative linear relation. If it's closer to +1, the stronger evidence is the positive association between the two variables. And if it's closer to -1, then there's a stronger evidence of a negative association between the variables. If far as close to zero, then there is little to no evidence that a linear relation between the two variables. So r close to zero does not imply relation, just no linear relation. So you can't say there will be no relation. It won't be like that dotted plot where you can tell the correlation between the two things. The linear correlation coefficient is a unitless measure of association. So the unit of measure for x and y plays no role in the interpretation of r. The correlation coefficient is not resistant, therefore an observation does not follow the overall pattern of the data, could affect the value of the linear correlation coefficient. So you've got perfect positive, strong positive, moderate positive, and you can kind of go through these and see all of them. Nonlinear, linear, moderate, negative, and things like that. Okay. This one, what would you think? Well, it's sort of going up left to right. I would probably say moderate, moderate positive or strong positive. It's one of the two probably. Determine the linear correlation coefficient of the drilling data. And so if we went, they go and factor, they calculate all of this, all of that, and obviously this is the sum of all this is this. And so if they divide it, they get this positive correlation. This is probably a strong one because it's so close to 1. Obviously, we can't do an in-class activity because we're not in class. Draw a scatter diagram. Okay, that's still the other thing. Testing for determine the absolute value of the correlation coefficient. Find the critical value in the table 2 for given sample size. If the absolute value of the correlation coefficient is greater than the critical value, then we say a linear relation exists between the two variables. Otherwise, no linear relation exists. Determine whether a linear relation exists between the two variables. So they would just go ahead and do the correlation between the jelly and depth. Critical value for n is 12, is 0.576. Since this is greater than this, a positive one exists. We're not going to use that table, so. According to the data observed by the Statistical Abstract of the United States, the correlation between the percentage of female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 94%. Does this mean there's a higher percentage of females? Does this mean there's a higher percentage of females with bachelor's degree causes a higher percentage of births to unmarried mothers? Certainly not. The correlation exists only because both percentages have been increasing since 1990. It is not the relation that causes the high correlation. In general, time series may not have correlation because each variable is moving in a specific direction over time, both going up and down over time, one increasing while the other one is decreasing over time. When data are observational, we cannot claim that a causal relation exists between the two variables. We can only claim causality when the data are collected through a designed experiment. Another way that two variables can be related even though they're not causal relations is through the lurking variable. A lurking variable is related both to explanatory and response variables. For example, ice cream sales and crime rates have very high correlation. Does this mean that local governments should shut down ice cream shops? No, the lurking variable is temperature. As air temperature rises, both ice cream sales and crime rates rise. So they're more likely to rob you during the summer. Lurking variable and bone density material. Because colas tend to replace healthier beverages with, they're talking about soda. Because colas tend to replace healthier beverages and colas contain caffeine and phosphoric acid, Researcher Catherine L. Tucker and her associates wanted to know whether cola consumption is associated with lower mineral density in women. The table lists the typical number of cans of soda consumed in a week and female neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. So the figure on the next slide shows the scatter plot of the data. The correlation between the colas per week and the bone density is negative 0.80. Critical value for N is 15 is the absolute value of this, which is 0.5, or I'm sorry, it's 0.514. Absolute value of that is 0.806. We conclude there is a negative correlation because exists between the colas consumed and the bone density. Can the authors conclude the increase in colas consumed caused a decrease in the bone density, mineral density? Identify some lurking variables in the study. So we don't know, for instance, anything about the health of these people before they took this. That could be a lurking variable. We don't know how much the people weigh. It could be something like that. And obviously in the cohort studies, data are collected from a group of subjects through questionnaires and surveys over time. Therefore, the data are observational, so researchers cannot claim that the increased cola consumption causes the decrease in bone mineral density. Some lurking variables are height, smoking, alcohol consumption, calcium intake, physical activity, and bone density. So the authors were careful to say that increased cola consumption is associated with lower bone mineral density because of the potential lurking variables. They never stated that increased cola consumption causes lower bone mineral density. And so that is that for this video. We'll get into the next one in the next